Everything in the universe is rotating. Every particle, every world, every galaxy, all of it carrying angular momentum that the laws of physics insist can never be erased. And yet when you measure the universe as a whole, its total rotation comes out to zero. Every part of it spinning, the whole thing perfectly motionless. That's either the most staggering coincidence in cosmic history, or it's a law of nature nobody has yet managed to explain. Either way, Kurt Gödel demonstrated that if that zero ever drifts, even by a hair, time travel stops being fiction and becomes physics, with consequences beyond anything you or I can fully imagine. If you're new here, welcome to Sundown Science. Hit subscribe and settle in. We're about to trace rotation from the smallest object in physics all the way out to the largest, and find out that the universe keeps flawless accounts of something whose origin it absolutely refuses to disclose. We'll also dig into why time travel isn't a wild idea at all, at least according to one mathematician's solution to an Einstein equation. Get comfortable and let's ease into it. Part 1. The hidden rotation you never notice. Nothing around you is at rest. Not the chair under you, not the floor beneath that, not the air drifting through the room, not the coffee going cold on the table, not the phone in your hand, not the walls that feel so fixed and permanent. Every single thing in the space around you, every object you've ever touched, ever stood on, ever leaned against, is moving. Not gently, not slowly, not in any way your body can register, but at a velocity that, if you could somehow climb out of the system and observe it from outside, would look like a precisely choreographed high-speed rotation, so vast and so smooth that from inside it feels like complete stillness. Right now, if you're anywhere near the equator of this planet, your body is being carried eastward at 1,674 kilometers per hour. That's faster than most military jets at cruise. That's faster than the speed of sound in air at sea level, which clocks in around 1,235 kilometers per hour. You are outrunning sound continuously in a direction you can't feel, on a rotating sphere that finishes one full revolution every 23 hours, 56 minutes, and 4 seconds. And you sense nothing. Not a breath of wind, not a tremor, not the faintest hint of motion. Just the ordinary static feeling room around you, humming quietly with the illusion that everything is at rest. The reason you feel nothing is one of the most elegant ideas in all of physics. It's called an inertial frame. When a system moves at a steady velocity, or in the case of Earth's rotation, when the rate of change in that velocity is gentle enough that your body can't register the acceleration, your nervous system has no way of telling the difference between sitting still and sitting on a conveyor belt cruising at 1,500 kilometers per hour. You aren't built to detect constant motion. You're built to detect changes in motion. The instant something accelerates or brakes hard, you feel it. But smooth, continuous rotation at a fixed rate? Your brain files it away as stillness. That's not a perceptual failure. It's an accurate description of your reference frame. From inside the rotating system, the physics is identical to being at rest. Only when you compare your reference frame against something outside it does the motion show itself. And here's what makes this genuinely strange. The atmosphere above you is doing the same thing. The oceans are doing the same thing. The jet streams cutting through the upper troposphere at altitudes of 10 to 12 kilometers are doing the same thing. Every layer of the system is co-rotating with the surface, dragged along by friction and gravity into a synchronized spin that keeps the whole envelope of air, water, and crust turning together as one coherent layered structure. The atmosphere doesn't spill off into space while the Earth rotates beneath it. It holds on. It rotates with the planet, gripped by gravity, firmly enough to keep trillions of tons of gas and liquid moving in lockstep with a sphere of rock and iron. The single place this co-rotation breaks down slightly, the one place you can actually witness Earth's rotation as a real, measurable physical effect, is in the behavior of large-scale weather systems. This is the Coriolis effect. When air masses try to travel in a straight line across the surface of a rotating planet, the planet's rotation deflects them. In the northern hemisphere, moving objects veer to the right. In the southern hemisphere, they veer to the left. Hurricanes and cyclones rotate counterclockwise in the north and clockwise in the south, not because of some intrinsic preference in fluid dynamics, but because the ground beneath them is rotating, and the Coriolis effect is the universe's method of making that rotation visible at the atmospheric scale. Every time you look at a satellite image of a hurricane, you're looking at proof that you're already inside a rotating reference frame. The spiral arms of the storm are a signature. They're Earth's rotation writing its name across the clouds. But even that is surface level, if you'll forgive the phrase, because the rotation doesn't end at the scale of planets and atmospheres. It goes all the way down. Buried deep in the physics of matter itself, at the deepest level we currently understand, sits a phenomenon called quantum spin, a property every fundamental particle carries, behaving mathematically and experimentally like a form of angular momentum, even though it can't be described as a particle literally rotating in space. And there's a beautiful, almost eerie signature of this quantum-level spin that you can detect, with the right gear, anywhere in the universe. It's called the hydrogen hyperfine transition. The hydrogen atom is the most abundant structure in the cosmos. Roughly 75% of all ordinary matter in the universe is hydrogen. Inside a single hydrogen atom, one electron orbits one proton, and both particles carry their own intrinsic quantum spin. Most of the time, the electron and the proton have their spins pointing in opposite directions, because that's the lower energy configuration. But every so often, the electron flips its spin to align with the proton instead, a slightly higher energy state, and then flips back. When it drops back into the lower state, it releases a photon. That photon has a very specific frequency, 1,420,405,751 Hz, 1.42 GHz, precisely. Not approximately, not roughly, exactly. It's so stable, so consistent, and so universal that radio astronomers use it as a standard beacon to map hydrogen gas across the galaxy. The universe is broadcasting this frequency from every hydrogen atom that has ever undergone this transition, meaning from nearly every corner of observable space. Every hydrogen atom in your body, in your water, in your proteins, in your DNA, in the fluid bathing your cells, is participating in a quantum rotational process. The spin of the electron and the proton isn't something that happens to hydrogen, it's a property of what hydrogen is. The rotation is built in, it's intrinsic. It doesn't need to be caused, triggered, or initiated. It just exists as a feature of matter at its most fundamental level. So let's be very clear about where we are so far. Your body is rotating at over 1,000 miles per hour on the surface of a planet. That planet is orbiting a star at 30 kilometers per second. The star is moving through the Milky Way at around 230 kilometers per second. The Milky Way itself is falling toward the Virgo cluster at roughly 600 kilometers per second. And at the bottom of all of it, inside the atoms that make up everything you can see or touch, there's a layer of intrinsic quantum spin that never stops, never winds down, and never requires any energy to maintain. Motion isn't something that happens in the universe. Rotation is the default. It's the ground state of matter embedded in gravitational systems. The still objects, the resting bodies, the motionless surfaces. These are all local illusions assembled by your reference frame. The universe, from the quantum scale to the galactic scale, doesn't do stillness. it does spin. And if that's true, if rotation is this fundamental, this universal, this persistent, then the question that ought to keep you up at night isn't why things spin. The question is whether anything, anywhere, ever stops. Part 2. The hierarchy of spinning things. There's a law in physics so foundational that it operates identically whether you're describing the spin of an electron or the orbital motion of a galaxy cluster. And it's this: angular momentum is conserved. That sentence sounds simple. It isn't. What it means, worked out to its full implication, is that any spinning or orbiting system that isn't acted on by an external torque, an external twisting force, will continue spinning or orbiting indefinitely, not gradually winding down, not eventually drifting to a halt, indefinitely. If you could strip away all friction, all drag, all gravitational disturbance, and leave a rotating body completely isolated, it would still be rotating in 1 trillion years, in 10 trillion years. At the heat death of the universe, if any matter remained and that matter had angular momentum, it would still be rotating. Conservation of angular momentum isn't a tendency or a rule of thumb. It's a precise, mathematically exact law that holds at every scale of physical reality we've ever tested. This is why the hierarchy of spinning things looks the way it does. Start at the bottom. Every fundamental particle, electron, quark, neutrino, photon, carries a property called spin. This is quantum spin, not classical rotation. We'll come back to it in detail because it really is one of the strangest things in all of physics. But for now, what matters is that it behaves like angular momentum. It's quantized, it's conserved, it's intrinsic to the particle, not something the particle picked up or could shed. Electrons have a spin of 1/2 in units of the reduced Planck constant. Protons have a spin of 1/2. Photons have a spin of 1. Higgs bosons have a spin of 0. These values never change. An electron is always a spin 1/2 particle. It cannot become a spin 0 particle. The spin is part of what the particle is. Move up one level. Atoms inherit angular momentum from the spins of their constituent particles and from the orbital angular momentum of electrons circling the nucleus. Molecules inherit angular momentum from their constituent atoms. These angular momenta combine and interact according to strict quantum mechanical rules, giving every molecular species a characteristic rotational signature, the same one that lets astronomers identify the composition of interstellar gas clouds from light years away by analyzing the specific microwave frequencies those molecules absorb or emit as they rotate. Move up to the planetary scale. The solar system formed from a collapsing cloud of gas and dust roughly 4.6 billion years ago. That cloud wasn't perfectly uniform. It had slight irregular motions, local variations in velocity caused by the turbulence of nearby supernova shockwaves, gravitational nudges from neighboring clouds, and the inherent messiness of fluid dynamics at astronomical scales. When gravity began pulling that cloud inward, those slight motions were dramatically amplified. Here's the physics of it. As a rotating object contracts, its rotation rate increases. This is the same principle that makes a spinning ice skater speed up when they pull their arms in. As the cloud collapsed, it spun faster. The faster it spun, the more centrifugal tendency pushed material outward in the plane perpendicular to the rotation axis. The result wasn't a sphere but a disk, a flat rotating structure called a protoplanetary disk, with the young sun at its center and the remaining material orbiting in increasingly organized rings around it. Planets formed out of the material in those rings, accreting mass through repeated collisions, inheriting the angular momentum of the disk as they grew. The Earth's rotation today is a direct echo of that original slight turbulence in a cloud of gas, billions of years before the planet ever existed. The spin was there before the planet was. The planet formed around the spin. Move up to the stellar scale. Stars form by the same process, just at a larger scale. A star-forming molecular cloud contracts under gravity, amplifying whatever angular momentum it began with. Young stars rotate rapidly. Some spin once every few hours, far faster than the Sun's current rotation period of roughly 25 days at the equator. Across millions and billions of years, stellar winds and magnetic field interactions gradually shed angular momentum, slowing the rotation. But the spin never disappears. It's redistributed. The Sun's rotation today, slower than in its youth, is still a conserved remnant of the angular momentum that was present in the interstellar gas before the solar system existed. Move up to the galactic scale. The Milky Way is a barred spiral galaxy roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. All those stars are orbiting the galactic center in roughly the same plane, in roughly the same direction, in a coherent rotating disk structure. The whole galaxy takes somewhere between 225 million and 250 million years to complete one rotation at the radius of the Sun. One rotation in the roughly 4.6 billion year lifetime of Earth. Our planet has completed only about 20 galactic orbits. For most of the universe's history, galaxies have been slowly turning through their rotations, building structure, redistributing matter, and doing what rotating systems under gravity always do: organize. The crucial conceptual point here is that angular momentum isn't created at any of these scales. It's inherited and redistributed. The spinning galaxy didn't generate its own spin from nothing. It acquired it from the angular momentum present in the matter that collapsed to form it, which acquired it from the turbulent rotating conditions of the early universe, which, and this is where the story gets complicated, had to acquire it from somewhere before that. Angular momentum is a cosmic memory system. Every spinning thing you see is carrying a historical record of motion that stretches back without interruption to conditions that existed before the object itself existed. Accretion disks are perhaps the most dramatic demonstration of this principle. Whenever matter falls toward a massive central object, a forming star, a neutron star, a black hole, it almost never falls in a straight line. Almost all infalling material has some angular momentum relative to the central object. As it falls inward, that angular momentum has to be conserved, which means the material can't simply pile onto the central object. Instead, it spirals inward, forming a disk. The disk rotates faster closer to the center and slower farther out. Material slowly migrates inward as angular momentum is transferred outward through the disk by magnetic instabilities and turbulent viscosity. The result is an accretion disk, one of the most energetic, luminous, and structurally elegant objects in astrophysics. And the engine driving the whole thing is nothing more exotic than conservation of angular momentum applied to infalling gas. Rotation isn't something that needs to be explained at each individual scale. It's the default outcome whenever matter with angular momentum exists in a gravitational potential. The real question, and we'll spend the rest of this documentary circling it, pun absolutely intended, isn't why these specific objects spin, but where the total angular momentum in the universe came from in the first place. And why, when you add it all up, the answer appears to be almost exactly zero. Part 3. The Galaxy Clock Problem. The dinosaurs never saw the same sky twice, not just in the sense that individual stars shift relative to one another over geological timescales, they do, but in a much more fundamental sense. The entire solar system, the Sun and all its planets, has been orbiting the center of the Milky Way for the entire 4.6 billion year history of Earth. And at the orbital speed we currently measure, around 230 kilometers per second, the solar system completes one full lap of the galaxy in roughly 225 to 250 million years. That unit of time even has a name, the galactic year or cosmic year. Earth is currently about 20 galactic years old. The Sun has finished roughly 20 laps around the Milky Way since the solar system formed. Each of those laps took as long as the entire Phanerozoic eon, all of complex animal life, all 5 mass extinctions, the entire Cambrian explosion, the rise of the mammals, the whole human story, to complete just one fraction of one orbit. When the non-avian dinosaurs went extinct 66 million years ago, the solar system had finished only about a quarter of a galactic orbit since the start of the Cretaceous. The Andromeda Galaxy, 2.5 million light-years away, is the farthest object you can see with the naked eye. By the time the light you see from Andromeda tonight first left its source, the solar system had barely budged in its galactic orbit. On cosmic timescales, even the galaxy is rotating slowly. But here's what's strange about galactic rotation, and it's strange in a way that turns out to point toward one of the deepest unsolved problems in all of physics. When you spin a solid object, a wheel, a plate, a disk, the entire structure rotates as a rigid body. The outer edges and the inner parts complete their rotations in the same amount of time. This is called solid body rotation. But galaxies aren't rigid. They're collections of hundreds of billions of gravitationally bound but essentially collisionless stars, each following its own orbit. And if all that mattered were the gravitational pull of the visible stars, gas, and dust in the galaxy, then the outer stars, the ones far from the dense central regions, should orbit more slowly than the inner ones. Just as the outer planets of the solar system orbit the Sun more slowly than the inner ones, because they feel weaker gravitational attraction from a mass concentrated near the center. The Swiss-American astronomer Fritz Zwicky noticed something off about galaxy clusters in the 1930s. The clusters were moving too fast internally to be held together by the gravity of their visible mass. But it was the American astronomer Vera Rubin who made the observation that locked the problem in beyond any reasonable denial. Working through the 1960s and 1970s, Rubin measured the rotation speeds of stars at different distances from the centers of galaxies. She expected to see the pattern predicted by Newtonian gravity applied to the visible mass, fast rotation near the center, slowing steadily toward the edges. Instead, she found something that shouldn't have been possible. The rotation curves were flat. Stars at the outer edges of galaxies were orbiting just as quickly as stars closer to the center. In some cases, the outer stars were even moving slightly faster. This is a profound violation of what the visible matter should permit. If you apply Newton's law of gravity to only the stars and gas you can see, the outer stars are moving far too fast to stay gravitationally bound to the galaxy. They should be flying off into intergalactic space. But they aren't flying off. They're orbiting at speeds that demand far more gravitational mass than is visible. Something is providing extra gravitational pull, something massive, distributed in a roughly spherical halo around the galaxy, present at the edges and in the outskirts where the visible stars are sparse. That something doesn't emit light, doesn't absorb light, doesn't interact electromagnetically with anything we've been able to detect. We know it exists only because its gravity is bending the rotation of galaxies away from what the visible matter predicts. We call it dark matter. Dark matter isn't a confirmed particle. It's a name for the gravitational problem, a placeholder for whatever is providing the extra gravitational scaffolding that holds galaxies together and produces the flat rotation curves Vera Rubin measured. Various candidate particles have been proposed over the decades. Weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. None has been directly detected. direct detection experiments buried deep underground to shield them from background radiation have been running for decades without a confirmed signal. There's an alternative hypothesis worth mentioning, one that mainstream cosmology treats skeptically but can't entirely dismiss. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983. MOND suggests that Newton's law of gravity breaks down at the very low accelerations typical of the outer regions of galaxies, and that a modified formula can account for the flat rotation curves without requiring any dark matter at all. MOND works remarkably well for individual galaxies. It works poorly for galaxy clusters, and it hasn't been successfully extended into a full relativistic theory that passes all the other tests general relativity passes. So it remains a minority position, an intriguing anomaly at the edge of the mainstream. What both hypotheses agree on is this: galactic rotation curves are telling us something we don't fully understand about the distribution of mass and gravity in the universe. Rotation, the thing we're tracking all the way from the electron spin in your hydrogen atoms to the spiral arms of the Milky Way, is acting as a diagnostic tool. It's revealing that the universe contains far more structure than we can see. The rotation is the fingerprint. The invisible mass is what left it. And if the mass distribution of galaxies is controlled by something we can't see, something whose origin and nature remain genuinely unknown after decades of searching, then the story of why everything spins has a chapter written in matter we've never detected, organized in a structure we don't fully understand, holding the visible universe in a rotational pattern that our best physics only partially explains, which is either deeply unsatisfying or deeply exciting, depending on your temperament. Personally, it's exactly the kind of thing that should keep you watching. Part 4. The first crack in intuition. Picture a collapsing cloud of gas. You've got a region of space a few light years across, full of hydrogen, helium, and traces of heavier elements. The gas is cold, it's diffuse, but it isn't perfectly uniform and it isn't perfectly still. It has slight density variations, slight velocity differences between different parts of the cloud, and at some point some perturbation, maybe a nearby supernova shockwave, maybe a gravitational interaction with another cloud, maybe just the accumulation of its own gravity over millions of years, causes the cloud to start contracting. Gravity is pulling everything inward toward the densest region. Now ask a simple question. What shape should the result be? Your intuition might say a sphere. Gravity is isotropic. It pulls equally in all directions toward the center, so a collapsing cloud ought to collapse into a sphere. And that's partly true for the final stellar object at the center, but what actually happens during the collapse is different. Because the cloud has angular momentum, those slight irregular motions we mentioned, the turbulent velocities across different parts of the cloud contain a net angular momentum. The cloud as a whole has a slight overall spin. Not much, but some. And as the cloud contracts, that angular momentum has to be conserved. The cloud can't shed it, it has nowhere to put it. So as the radius of the collapse decreases, the rotation rate climbs to compensate. The rotation rate climbs dramatically. If the original cloud had a radius of a few light years and a slow, barely detectable rotation, and it collapses to a disk a few hundred astronomical units across, the rotation rate increases by a factor proportional to the square of the ratio of the radii. That's an enormous amplification. The rotation that was imperceptible in the diffuse cloud becomes the dominant organizing force in the collapsing system, powerful enough to halt the collapse perpendicular to the rotation axis. This is the key insight. Rotation doesn't just accompany gravitational collapse, it actively shapes the outcome. Material falling in along the rotation axis falls all the way to the center, forming the protostar. But material falling in from the sides can't fall all the way in because it carries angular momentum that keeps it from moving straight toward the center. Instead, it spirals inward, conserving its angular momentum, and settles into a rotating disk around the central object. The disk isn't a coincidence or an accident, it's the mathematically inevitable result of angular momentum conservation acting on a collapsing system. This is why planets form in disks, not in random three-dimensional distributions around their host stars. This is why the rings of Saturn are flat. This is why accretion disks around neutron stars and black holes are flat. This is why galaxies form as disks rather than spheres. The disk shape isn't a preference of gravity. Gravity alone would produce a sphere. The disk shape is the signature of angular momentum conservation, overriding the spherical symmetry of gravity in the plane perpendicular to the rotation axis. Every disk structure in the universe is a record of a rotation that existed before the disk formed. Now consider what this means for non-rotating systems. In theory, if you had a perfectly non-rotating cloud of gas with exactly zero angular momentum, it could collapse to a sphere without forming a disk. And in theory, perfectly non-rotating systems can exist. But in practice, in the messy, turbulent, gravitationally interactive real universe, perfectly zero angular momentum is extraordinarily unlikely. Any slight motion, any tiny perturbation, any minuscule velocity gradient across the cloud will survive the collapse and get amplified into a visible rotation. The universe's physical systems find it almost impossible to arrive at exactly zero angular momentum, because any process that could set angular momentum to zero would require a very specific, very finely tuned cancellation of motions that random dynamical processes essentially never produce. This is the first crack in the intuitive picture of rotation. Rotation isn't something that needs to be added to the universe's systems. It's the default. The only thing that would require explanation is the absence of rotation. A non-rotating star, a non-rotating planet, a non-rotating galaxy, these would be the anomalies. Rotation is what you get when you start with a cloud of gas that has any angular momentum at all and let gravity do its work. And this raises a question that the first act of this documentary is quietly building toward answering, or rather, toward demonstrating can't yet be answered. If rotation is the default outcome, if every system that forms under gravity inevitably rotates because it can't help but amplify whatever angular momentum it started with, then the most important question in this whole story isn't about the mechanisms of rotation. Those are understood, at least in outline. The important question is about the origin of the angular momentum that gets amplified. Where did the first angular momentum in the universe come from? What seeded the rotational content that every spinning galaxy, every orbiting planet, every precessing quantum particle is still carrying today? The universe's rotational ledger shows billions of entries, every single one of them a spinning, orbiting, precessing structure. But no entry in the ledger records the initial deposit. And as we're about to discover, the rules of physics that govern how angular momentum behaves don't have anything to say about where it came from. They only guarantee that wherever it came from, it has been preserved perfectly ever since. The rules of spin go much deeper than planets and galaxies. They go all the way down into a layer of reality where rotation stops being a motion at all and becomes something closer to the definition of matter itself. Part 5. The Stern-Gerlach shock. In 1922, two German physicists named Otto Stern and Walter Gerlach performed an experiment that, if you understood what they were expecting to find versus what they actually found, should have made you immediately question everything you thought you knew about the structure of matter. The setup wasn't complicated. Stern and Gerlach took silver atoms, single atoms, vaporized from a heated sample, and passed them through a region of strongly non-uniform magnetic field. The logic was classical and intuitive. A silver atom has a magnetic moment, meaning it acts like a tiny bar magnet. In a non-uniform magnetic field, a magnet gets pushed or pulled depending on how its magnetic axis is oriented relative to the field gradient. A magnet pointing directly along the field gets pushed one way. A magnet pointing opposite to the field gets pushed the other way. A magnet pointing sideways gets deflected less, and a large collection of atoms, which classically should have their magnetic moments oriented in every possible direction because there's no reason to prefer one orientation over another, should produce a continuous smear of deflections on the detector plate. Some atoms deflected a lot upward, some deflected a lot downward, and everything in between, forming a continuous band. What Stern and Gerlach found was two spots, not a band, not a continuous smear. Two discrete separated dots on the detector plate. Half the atoms were deflected one way, the other half were deflected the opposite way. Not continuously distributed, not gradually spread. Split sharply into two, and only two possible outcomes, as though the magnetic moment of the silver atom could take only one of two values and nothing else. This was a direct experimental proof that something about atomic angular momentum was quantized, restricted to discrete values rather than allowed to vary continuously. The concept wasn't entirely new in 1922. Niels Bohr had already proposed quantized energy levels for the hydrogen atom a decade earlier, and the idea that quantum systems preferred discrete states over continuous ones was already in the air. But the Stern-Gerlach experiment made it viscerally concrete. You could see the quantization with your eyes. There was a gap on the detector plate between the two spots, where the atoms would have landed if they had intermediate orientations. That gap was proof that intermediate orientations did not exist. What was slightly embarrassing historically was that the experiment worked for reasons that weren't fully understood at the time. Stern and Gerlach thought they were measuring the orbital angular momentum of the outer electron in the silver atom. But the calculation for orbital angular momentum didn't predict just two discrete beams. Orbital angular momentum quantum numbers produce an odd number of possible orientations, 1, 3, 5, and so on. Never exactly 2. Two beams implied something with a quantum number of 1/2, which orbital angular momentum couldn't produce. It took 3 more years before Samuel Gaudsmit and George Uhlenbeck proposed the explanation. The electron itself had an intrinsic angular momentum, spin, separate from any orbital motion, with a value of 1/2 in units of the reduced Planck constant. A spin of 1/2 gives exactly 2 possible measurement outcomes, spin up or spin down, and there's nothing in between. The lesson here connects directly back to the story we've been tracing: rotation, the thing that organizes everything from protoplanetary disks to spiral galaxies, turns out at its most fundamental level to be quantized. It doesn't come in arbitrary amounts. It comes in discrete packets governed by precise algebraic rules, with no continuous transitions allowed. The universe doesn't permit half-integer spin particles to smoothly rotate from one orientation to another. They jump. They snap. And before the jump happens, the particle doesn't have a definite spin orientation at all. It's in a superposition of both, and only the act of measurement forces it to choose. If classical intuition was already strained by the idea that everything is rotating, it's about to break entirely. Because the spin that makes the Stern-Gerlach experiment work isn't the spin of a small sphere rotating in space. It's something much stranger than that. Part 6. The Impossible Electron. In 1925, 2 young Dutch physicists, Samuel Gaudsmit and George Uhlenbeck, were graduate students working with Paul Ehrenfest in Leiden when they proposed an idea that, the moment they tried to work out the details, should have been impossible. But it wasn't impossible. It was correct. The idea was this: the electron has intrinsic angular momentum. It behaves as though it's spinning. This would explain the anomalous Zeeman effect, which had been puzzling spectroscopists for decades. The mysterious splitting of atomic spectral lines in a magnetic field that didn't match the predictions of orbital angular momentum alone. If the electron had its own spin contributing its own magnetic moment, the extra splitting would make sense. But here's the problem they immediately ran into. If you try to model the electron as a small classical charged sphere spinning on its axis, which is the obvious physical picture of what intrinsic angular momentum means, the mathematics forces you into a contradiction. To generate a magnetic moment of the measured size with a sphere the size estimated for the electron at the time, the surface of that sphere would need to be rotating at a speed enormously greater than the speed of light, not slightly exceeding the speed of light, not ambiguously close to it, faster by several orders of magnitude. Since special relativity prohibits any object with mass from reaching the speed of light, let alone exceeding it by a factor of hundreds, the classical spinning sphere model was immediately and completely ruled out by its own mathematics. Goudsmit and Uhlenbeck actually tried to withdraw the paper. After working this out, they brought their calculation to Ehrenfest, who had already submitted the paper for publication, and told him they'd found a problem. Ehrenfest reportedly told them something along the lines of, "You're both young enough that you can afford to have a stupid idea." It turned out the idea wasn't stupid. The problem wasn't the spin, the problem was the model. The electron isn't a small spinning sphere. Modern physics treats the electron as a point particle, an entity with no spatial extent at all, no surface, no radius. A point can't spin in any geometrically meaningful sense. You can't define a rotation axis for something that occupies no space. And yet the electron has angular momentum, exactly 1/2 unit, always. Measured identically regardless of how fast the electron is moving, what environment it's in, or what experiment you use to probe it. The spin isn't a property of the electron's shape or its motion. It's a property of the electron's quantum state, an intrinsic attribute as fundamental as its mass or charge. The theoretical framework that made this completely coherent rather than merely empirically unavoidable came from Paul Dirac in 1928. Dirac was attempting to write a quantum mechanical equation for the electron that was consistent with special relativity. The Schrödinger equation worked well at low velocities but broke down relativistically. When Dirac wrote his equation, imposing the requirements of Lorentz invariance, the equation naturally and unavoidably produced a 4-component wave function. Not because Dirac put it in, but because the mathematics of combining quantum mechanics with special relativity demanded it. 2 of those components described the electron with spin up and spin down. The other 2 described a particle with the same mass but opposite charge, the positron, which was experimentally discovered 4 years later and won Carl Anderson a Nobel Prize. Dirac predicted antimatter without looking for it, as a mathematical byproduct of taking spins seriously at the relativistic level. What the Dirac equation says, in essence, is that spin isn't an optional feature of the electron. It isn't something you can remove or modify. It's a necessary consequence of combining quantum mechanics and special relativity. Any point particle described by a relativistic quantum theory must have spin. The spin 1/2 of the electron is as inevitable mathematically as the charge of the electron or the existence of antimatter. It falls out of the structure of the theory whether you want it to or not. So here's where we are. The rotation we've been tracking through galaxies and solar systems and accretion disks, that rotation exists because angular momentum is conserved, and every bound gravitational system preserves the angular momentum it inherited from the cloud that preceded it. But at the base of the entire tower, at the level of the particles from which all that matter is built, the rotation isn't inherited from anything. It's intrinsic. It's built into the mathematical structure of what a particle is. The electron doesn't spin because something set it spinning. The electron spins because not spinning is mathematically impossible for something described by the Dirac equation in a relativistic quantum universe. Rotation at the deepest level isn't a behavior of matter, it's part of the definition of matter itself. Part 7. Why matter exists at all. Here's a thought experiment that sounds absurd but is completely serious. Imagine removing spin from the universe, not just slowing things down, not just reducing angular momentum, but removing the intrinsic quantum spin of fundamental particles entirely. Setting spin to 0 for everything. What happens? The answer is, matter as we know it ceases to exist, not in some metaphorical or theoretical sense, literally. The physical properties of matter that allow it to form solid objects, chemical compounds, stable atoms, and complex molecules are all consequences of quantum spin. Take away the spin, and you take away the foundation that the entire material world is built on. The specific mechanism is called the Pauli exclusion principle, and it's one of the most powerful organizing principles in all of physics. It was formulated by Wolfgang Pauli in 1925, the same year Goudsmit and Uhlenbeck proposed electron spin, and the connection between the two isn't a coincidence. The Pauli exclusion principle states that no two identical fermions, no two particles with half-integer spin, can occupy the same quantum state simultaneously. Same position, same energy, same spin orientation, forbidden. Two electrons can be in the same atomic orbital only if they have opposite spins, because then they aren't in identical quantum states. The moment both electrons would need to have the same spin to occupy the same state, the Pauli exclusion principle prevents it. This rule has consequences that cascade through all of chemistry and all of solid-state physics. Consider what it means for atoms. The electrons around a nucleus can't all pile into the lowest energy level. The first level can hold two electrons with opposite spins. Then it's full. The next electron has to go to the second energy level. The third and fourth electrons go into that level, then the remaining spots in the second shell fill up, and eventually those are full too. Every additional electron has to occupy a higher energy level farther from the nucleus, with different spatial distribution. The result is the shell structure of atoms, and the shell structure of atoms is exactly what produces the periodic table. Chemistry exists because electrons have spin 1/2 and obey the Pauli exclusion principle. The patterns of chemical reactivity, the valence electrons at the outer shells, the way atoms combine and share electrons to fill their outer shells, all of this is determined by the shell structure, which is determined by the exclusion principle, which is determined by the half-integer spin of electrons. Without spin, all electrons would collapse into the lowest energy level. All atoms would have the same electronic structure. All elements would be chemically identical. There would be no periodic table, no chemical bonds, no molecules, no carbon, no water, no organic chemistry, no biochemistry, no life. The exclusion principle also explains why matter takes up space. Why doesn't your hand pass through the table when you press down on it? Not because atoms are solid spheres that can't overlap. The vast majority of atomic volume is empty space. The reason is electron degeneracy pressure. When two atoms get pushed close enough together that their electron clouds begin to overlap, the electrons from different atoms would be forced into the same spatial region. But they can't occupy the same quantum state, so they resist. The Pauli exclusion principle generates an effective repulsive force, not an electromagnetic force, not a gravitational force, but a purely quantum mechanical consequence of half-integer spin statistics that prevents electron clouds from interpenetrating. This force is what gives matter its solidity. This force is what keeps your hand on the surface of the table rather than passing through it. In extreme environments, this principle takes on even more dramatic significance. When a sufficiently massive star runs out of nuclear fuel and collapses, the weight of the entire stellar mass compresses the core. In a white dwarf, the remnant of stars like the Sun, the collapse is halted by electron degeneracy pressure. The electrons can't be pushed into the same quantum states, and this resistance supports the star against further gravitational collapse, even without any nuclear burning. In a neutron star, the collapse is even more extreme, and its neutron degeneracy pressure, the same principle applied to neutrons, which are also spin 1/2 particles, that halts the collapse and supports the star. The stars that survive their deaths by becoming white dwarfs and neutron stars do so because of quantum spin statistics. So the Pauli exclusion principle, rooted in the half-integer spin of fermions, is responsible for the structure of the periodic table, the existence of chemical bonds, the solidity of matter, the floor you're standing on, the stability of white dwarfs and neutron stars, and every piece of structure in the universe that resists gravitational collapse. That isn't a peripheral consequence of spin. That's reality's entire physical architecture, built on a foundation of quantum angular momentum, which means rotation, not classical rotation of wheels and galaxies, but the intrinsic quantum spin of particles, isn't just a feature of the universe. It's the load-bearing structure of the universe. Without it, everything collapses into a uniform, featureless plasma. With it, you get chemistry, structure, complexity, and eventually observers curious enough to wonder why everything spins. Part 8. Spin as a bookkeeping law of reality. There's a theorem in quantum field theory called the spin statistics theorem, and it's unusual among physical theorems for a specific reason. It can't be explained intuitively, not just in the sense that it requires mathematical training to appreciate fully, intuitively. Richard Feynman, one of the most gifted physics explainers of the 20th century, said explicitly that he couldn't give you an elementary explanation of the spin statistics theorem. He tried multiple times. He couldn't find a way to make it feel obvious or motivated from simple principles. All he could say was that the derivation worked. The result was correct, and the correct result was that particles with half-integer spin must obey Fermi-Dirac statistics and the Pauli exclusion principle, while particles with integer spin must obey Bose-Einstein statistics and have no exclusion principle at all. This division, fermions versus bosons, half-integer versus integer spin, exclusion versus condensation, isn't one of several possible ways to organize particles. It's the only way. Every particle in the universe falls into one of these two categories, and the category is determined entirely by the particle's spin. Quarks are fermions, electrons are fermions, protons and neutrons are composite fermions, photons are bosons, gluons are bosons. The Higgs boson is a boson. Gravitons, if they exist as quantized particles, would be bosons. There's no third category. There's no continuous interpolation between the two. Spin determines statistics, and statistics determines how particles behave collectively, and how particles behave collectively determines the entire structure of matter and radiation in the universe. Why does spin determine statistics? This is where the spin statistics theorem comes in. The formal proof requires Lorentz invariance, the requirement that physical laws look the same in all inertial reference frames, combined with the requirements of quantum field theory that quantum fields must commute or anti-commute at space-like separations to preserve causality. If a field commutes with itself at space-like separations, the particles it describes are bosons. If it anti-commutes, the particles are fermions. And it turns out that fields describing half-integer spin particles must anti-commute. They have no choice if the theory is to be Lorentz invariant and causal. The anti-commutation relation is exactly what produces the Pauli exclusion principle. The mathematics locks it in. What this means conceptually is that spin isn't just a property particles happen to have. Spin is a constraint that spacetime imposes on quantum fields. The requirement that physics obey the symmetries of special relativity, specifically the symmetry under Lorentz transformations, forces quantum fields to carry specific spin values and forces those spin values to determine statistical behavior. Spin is, in a very precise sense, the signature of Lorentz symmetry at the level of individual particles. It's the answer to the question, what properties must a quantum field have if it's to transform consistently under the rotations and boosts of special relativity? The answer is, it must have a specific spin, and that spin must be either an integer or a half integer, and the spin determines everything about how particles of that field interact with each other. Consider the gauge fields of the standard model. The photon, which carries the electromagnetic force, has spin 1. The gluons, which carry the strong nuclear force, have spin 1. The W and Z bosons, which carry the weak force, have spin 1. All force-carrying particles in the standard model are spin 1. The graviton, the hypothetical carrier of gravity, would be spin 2 if it exists as a quantized particle. The Higgs boson, which gives mass to other particles, is spin 0. The pattern here isn't accidental. The spin of the force-carrying particle determines the mathematical structure of the force it mediates, the angular dependence of its interactions, the number of independent polarization states it can have, the way it couples to matter fields. Spin is the organizational principle of the entire standard model. And sitting underneath all of this, the exclusion principle, the periodic table, the solidity of matter, the structure of forces, the classification of particles, is a conservation law. Spin, as a form of angular momentum, is conserved. In every interaction, every collision, every decay, every emission, the total angular momentum is the same before and after. The universe keeps perfect books on its spin budget. Not a unit of angular momentum is ever created or destroyed. Every spin you could measure in every particle in the universe today is a spin that has been present in some form since the beginning. Which brings us back to the central question that this entire documentary is assembling, piece by piece. If spin is conserved, and if every spinning thing in the universe today inherited its spin from the previous configuration, and if the chain of inheritance stretches all the way back to the earliest moments of the universe, then whatever spin existed at the very beginning has been preserved perfectly, redistributed, but never created or destroyed, right up to the present moment. The angular momentum you can detect in the spin of an electron in your body right now is angular momentum that was present in the quantum fields of the early universe, encoded in the initial conditions of reality itself. And here's the question that physics cannot currently answer. Why did those initial conditions contain the specific angular momentum they did? Why not more? Why not less? Why not zero? What mechanism, if any, determined the opening balance in the universe's spin ledger? Because the laws of physics, as we understand them, can only tell you how the ledger evolves. They cannot tell you why it started with any particular entry. The universe keeps perfect books. But nobody has found the first deposit slip. Verash, Part 9. The Angular Momentum Paradox of Creation. Conservation laws are simultaneously the most powerful and the most unsatisfying tools in physics. They're the most powerful because they're exact and universal. They hold everywhere, in every process, at every scale, without exception. They're unsatisfying because conservation tells you about the evolution of a quantity, not about its origin. The law of conservation of angular momentum tells you that whatever angular momentum exists in the universe now must equal whatever angular momentum existed before, and before that, and before that, all the way back to the beginning. But it doesn't and can't tell you why the universe began with any particular amount of angular momentum. This creates what might be called the angular momentum paradox of creation. On one hand, every spinning galaxy, every orbiting planet, every rotating star, every precessing quantum particle is carrying angular momentum that has been conserved since the universe's earliest moments. On the other hand, the inflationary epoch, the period of extraordinary exponential expansion in the first tiny fraction of a second of the universe's existence, should have diluted any pre-existing global rotation to an undetectable level. Inflation expanded the volume of the universe by an almost incomprehensible factor, at minimum on the order of 10 to the power of 78 in volume, and possibly vastly more. If there were a net global angular momentum in the pre-inflationary universe, inflation would have stretched it across a volume so enormous that its density would be effectively zero in the observable universe. So where did the angular momentum of individual galaxies, stars, and planets come from? The answer is tidal torque theory, developed by Fred Hoyle in 1951 and extended by Peebles and others. The idea is that galaxies acquire their angular momentum not from some primordial global spin, but from gravitational interactions during the process of structure formation. In the early universe, after inflation, the distribution of matter wasn't perfectly uniform. There were slight density perturbations, overdense and underdense regions, seeded by quantum fluctuations during inflation, frozen in by the rapid expansion, and imprinted on the matter distribution as a tiny but real map of density variations. As gravity began collapsing these overdense regions into the seeds of future galaxies and galaxy clusters, neighbouring structures exerted gravitational tidal forces on each other. These tidal forces could exert torques, twisting forces, that transferred angular momentum between the proto-galactic structures. The key point is that angular momentum wasn't created in this process, it was exchanged. Two proto-galactic structures sitting near each other in the early universe could exchange angular momentum through tidal gravitational interactions. One gains spin in one direction, the other gains spin in the opposite direction. The total is unchanged. The net angular momentum of the universe remains what it was. But locally, individual structures acquire spin, not from any primordial global rotation, but from the mutual gravitational interactions of neighbouring mass concentrations. This is the standard model for how galaxies acquire angular momentum, from tidal torques during structure formation. But there are gaps. The quantitative predictions of tidal torque theory match the broad statistics of observed galaxy spins reasonably well, but not in detail. The theory has trouble predicting the spin magnitudes and orientations of individual galaxies with precision. There are correlations between galaxy spins and the large-scale cosmic web, the network of filaments and voids that galaxies are strung along, that aren't fully explained by simple tidal torque theory. The origin of galactic angular momentum is understood in outline, but the details remain an active research area. What the whole picture tells us, though, is something important about the rotational content of the universe. The angular momentum of every spinning structure you can see is ultimately traceable to quantum fluctuations in the inflationary epoch, amplified by gravitational collapse, exchanged between structures by tidal torques, and precisely conserved at every step. The spin of a galaxy is, in a very real sense, the grown-up version of a quantum hiccup in the first fraction of a second of time. The universe converts quantum noise into cosmic structure, and the rotation is part of that structure. But the question of why that noise contained the angular momentum it did, why the initial conditions were what they were, remains genuinely open. Part 10. The universe that cancels itself. Here's the statistic that should stop you cold. Add up the angular momentum of every galaxy in the observable universe. Every galaxy spinning in its particular direction, at its particular speed, with its particular mass. Then add up all the orbital angular momentum of galaxies within galaxy clusters, moving around their common centers of mass. Then add the spins of all the stars, all the planets, all the rotating neutron stars, all the spinning black holes. Add every spin at every scale. Do the full accounting. The answer is, to within measurement error, 0, not small. Not approximately 0 in the way that any large number divided by an enormous volume becomes small. 0 in the sense that the positive angular momenta and the negative angular momenta cancel each other with extraordinary precision. Galaxies spin in both directions in roughly equal numbers. Galactic orbits in clusters are oriented randomly, not preferentially in one direction. The large-scale universe shows no preferred rotation axis, no direction in which more angular momentum points than any other direction. The cosmic microwave background, the afterglow of the hot early universe that fills the sky uniformly from all directions, shows no asymmetry that would indicate a global rotation. The statistical isotropy of the observable universe isn't exact at the quantum fluctuation level. The CMB has real temperature variations of about 1 part in 100,000, but there's no large-scale pattern in those variations that looks like rotation. The universe is full of local rotation, and globally it isn't rotating. Every piece spins. The whole does not. This is deeply strange when you think about it carefully. It isn't at all obvious why this should be the case. You could imagine a universe in which the initial conditions happen to have a net angular momentum. A universe that, in addition to expanding, was slowly rotating as a whole. There's nothing in the laws of physics that obviously forbids this. General relativity permits rotating universe solutions. We'll come to one of them shortly, and it's a truly uncomfortable solution. The fact that we appear to live in a non-rotating universe is, from one perspective, a statement about the initial conditions of the universe. The conditions at the beginning were set up with extraordinary precision to give a net global angular momentum of essentially 0. Why? There's no known mechanism that requires this. There's no symmetry principle that obviously demands 0 net angular momentum for the universe as a whole. Some cosmologists argue that it might be a consequence of inflation, which would smooth out any large-scale rotation the way it smooths out any large-scale curvature or matter non-uniformity. But tidal torque theory produces local angular momentum without any net global angular momentum, so in some sense the cancellation could be a statistical consequence of the way angular momentum is distributed rather than a deep symmetry principle. Different structures got their angular momenta from tidal interactions with neighbours, and those interactions automatically conserved the total, ensuring equal and opposite spins across the whole. But the precision of the cancellation is still striking. The observable universe contains something like 2 trillion galaxies, and they cancel each other's spin to within our best measurement capability. There's a beautiful and slightly eerie quality to this. A universe in which every individual component is restlessly spinning, but the aggregate is perfectly still, like a gyroscope that's spinning internally but not precessing, or like a collection of spinning tops arranged so that their angular momenta point in every possible direction, and when you take the vector sum, all the arrows cancel to a point. The universe is doing this not with a few spinning tops, but with the angular momentum of every galaxy in a volume 10 billion light-years across. And it's doing it, apparently, by accident. Or is it? The possibility that the cancellation isn't quite perfect, that there's a tiny residual global angular momentum hiding at a level just below current detection thresholds, is genuinely scientifically open. And if that possibility is real, the implications aren't just astrophysical, they're existential. Part 11. Is the universe secretly rotating? The question of whether the universe has a small but non-zero global rotation isn't merely academic. It's a test of the most fundamental assumptions of modern cosmology and a potential window into conditions at the very beginning of the universe. Modern cosmology rests on an assumption called the cosmological principle, that the universe, on the larger scales, is homogeneous and isotropic. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. These are approximations, of course. The universe clearly has structure at smaller scales, with galaxies clustered into filaments and voids. But on scales of a few 100 million light-years and larger, the universe does appear to be remarkably uniform. The cosmological principle is supported by the isotropy of the cosmic microwave background, which varies by less than 1 part in 100,000 across the sky. A rotating universe would be anisotropic. It would have a preferred axis, and physics would look different along that axis than perpendicular to it. The extraordinary isotropy of the CMB is the primary observational argument against any significant global rotation. The Planck satellite, which provided our most precise maps of the cosmic microwave background, has set extremely tight limits on possible global rotation. The upper bound on the rotation rate of the universe is something like 10 to the power of -9 radians per Hubble time, meaning that if the universe is rotating at all, it completes at most 1/1000th of a radian of rotation over the entire age of the universe. That's not just slow. It's so slow that the word slow doesn't adequately capture it. The entire observable universe has expanded, structured itself into galaxies and galaxy clusters and cosmic webs of filaments, produced stars, planets, and observers. And in all that time, if there's any global rotation at all, the universe hasn't even finished 1/10 of 1/1000th of a full rotation. For practical purposes, this is zero. But it isn't proven to be exactly zero. There have been claims, controversial and not universally accepted, of observational hints at cosmic anisotropy. Leo Shamir, a computer scientist and astronomer, published several studies analyzing large catalogues of galaxy images and arguing that galaxies rotating in one direction appear to outnumber galaxies rotating in the other direction by a small but statistically significant margin. About 3% more clockwise rotating than counterclockwise rotating spirals, or vice versa, depending on which part of the sky you look at and which dataset you use. If this asymmetry were real and systematic, it would imply a preferred handedness in the universe's structure, a subtle global chirality, or possibly a weak global rotation imposing a slight preference on the angular momenta of forming galaxies. Most cosmologists are skeptical. The claimed asymmetries are small, the statistical methodologies are disputed, and systematic biases in how galaxy images are classified, particularly in automated image analysis systems, which can have subtle asymmetric errors in how they assign rotation directions, are a plausible alternative explanation. The debate hasn't been resolved as of the present, and it probably requires future, larger, more carefully controlled surveys to settle definitively. But the fact that the debate exists at all, that serious observational work is being done to constrain the global rotation of the universe at the level of parts per billion, tells you something important about the stakes involved. A non-rotating universe is the foundational assumption of the standard cosmological model. If that assumption turned out to be even slightly wrong, if there were a genuine, measured, reproducible global rotation at any non-zero level, it would not just require revision of some details of the model, it would force a complete reconsideration of the cosmological principle and everything built on it. And it would raise a question that goes well beyond astrophysics, because, as we're about to see, a rotating universe isn't just a different kind of universe. A rotating universe is a universe where the arrow of time may point in more than one direction simultaneously, and that's a problem that even general relativity cannot easily contain. Part 12. Gödel's Rotating Universe Nightmare. On April 28, 1949, Kurt Gödel presented a paper at a conference in Princeton to celebrate Albert Einstein's 71st birthday. Gödel was already famous, having published his incompleteness theorems in 1931, which demonstrated that any sufficiently powerful formal mathematical system must contain true statements that can't be proved within that system. He had destroyed the program of finding a complete and consistent foundation for all of mathematics in two theorems that fit on a few pages. Now, at Einstein's birthday conference, he had found an exact solution to Einstein's field equations of general relativity, and it described something that should not be possible. Gödel's solution described a rotating universe. In this universe, matter was uniformly distributed throughout space, as in standard cosmological models. But the matter was rotating. And in this rotating universe, a sufficiently motivated traveler could, by following a specific path through spacetime, accelerating, curving, and returning, arrive back at the same point in space and the same moment in time they had started from. Not the same location after a long journey, the same moment, a closed time-like curve, a path through space-time that loops back to its own origin in time. What Gödel had found was that a rotating universe contains closed time-like curves, meaning that in such a universe, travel into your own past isn't just theoretically conceivable, but physically permitted by the laws of general relativity. The rotation of the universe creates a gravitomagnetic-like effect on the structure of space-time. It twists the light cones, the structures that define which events can causally influence which other events, in a direction that allows curves through space-time to close on themselves. In a non-rotating universe, the causal structure is clean. Your past light cone contains all events that could have influenced you, and your future light cone contains all events you could potentially influence. In a rotating universe, those cones can tilt enough that a path forward in time can curve around and arrive at its own starting point. This is deeply, uncomfortably problematic. Closed, time-like curves allow causal paradoxes of the type you've probably encountered in science fiction, going back in time to prevent your own birth, or killing your grandfather before your parents were conceived. More technically, they violate the chronological protection conjecture, Stephen Hawking's hypothesis that the laws of physics conspire to prevent the formation of such curves in any physically realizable scenario. Hawking believed this had to be true because the alternative, a universe where causality could be violated, seemed not just counterintuitive, but catastrophically inconsistent. Now, to be very clear, our universe doesn't appear to be the Gödel universe. We don't observe global rotation. We don't observe closed time-like curves. Cosmological observations are consistent with a non-rotating, expanding universe governed by the standard model of cosmology. Gödel's solution is a curiosity, a demonstration that general relativity permits rotating solutions, not evidence that we live in one. Stephen Hawking and Roger Penrose worked extensively on proving that physically reasonable rotating universes either must collapse or develop other pathological features that prevent the formation of closed, time-like curves in practice. But here's why Gödel's nightmare matters for this story. The fact that a rotating universe would allow time travel, that global rotation and causal structure are linked through general relativity in this very specific and uncomfortable way, gives you a completely different perspective on why the zero-net, angular momentum of our universe might not be a coincidence. If the universe had started with significant global rotation, the causal structure of space-time itself could have been compromised. The arrow of time, which we experience as pointing relentlessly forward and which underlies every physical process we know, might not exist in the same clean, universal way. The ordinary picture of cause preceding effect of the past being fixed and the future being open could become muddied. So perhaps the precise cancellation of global angular momentum in our universe isn't just an interesting cosmological fact. Perhaps it's a necessary feature of a universe where time works the way time has to work for complexity, for chemistry, for evolution, for consciousness, for anything at all to be possible. Perhaps we live in a non-rotating universe not by accident, but because a rotating universe would be too broken to be inhabited. Or perhaps the cancellation is genuinely accidental, a product of how angular momenta were distributed during structure formation, and the connection to causal structure is a mathematical warning that we happened, by cosmic luck, to avoid triggering. Either way, the zero is doing a lot of work, and as we're about to discover, the question of where it came from and what is holding it in place goes all the way to the deepest levels of physical law we have ever articulated. Part 13. Rotation as Symmetry Consequence. There's a theorem in mathematical physics that is simultaneously the most powerful and the most philosophically haunting result in all of science. It was proved in 1915 by the German mathematician Noether, and it states in its most general form that every continuous symmetry of the laws of physics corresponds to a conserved quantity. If the laws of physics are symmetric under translations in time, if the rules work the same today as they did yesterday and will tomorrow, then energy is conserved. If the laws of physics are symmetric under translations in space, if the rules work the same here as they do 1 meter to the left or 1 light year away, then momentum is conserved. And if the laws of physics are symmetric under rotations in space, if the rules work the same regardless of which direction you point your experiment, then angular momentum is conserved. Noether's theorem is extraordinary because it makes conservation laws feel inevitable rather than arbitrary. Energy conservation isn't a coincidence or an empirical fact we happen to measure and then wrote down. It's a mathematical consequence of the fact that physics doesn't change over time. Momentum conservation is a mathematical consequence of the fact that physics doesn't change depending on where you are. Angular momentum conservation is a mathematical consequence of the fact that physics doesn't have a preferred direction. The laws of physics look the same if you rotate your reference frame by any angle. This rotational symmetry, called SO3 in the language of mathematics, the group of rotations in three-dimensional space, appears to be an exact symmetry of nature, not an approximate symmetry that holds to within current measurement precision. An exact symmetry, meaning that as far as any experiment has ever been able to test, there is genuinely no preferred direction in the laws of physics. And because this symmetry is exact and continuous, Noether's theorem guarantees that angular momentum is conserved exactly and completely in every physical process. This is why the rotational conservation we've been tracing through this entire documentary holds. From the quantum spin of an electron in your hydrogen atoms, to the rotation of the protoplanetary disk that built the Earth, to the orbital motion of the solar system around the Milky Way, angular momentum has been conserved in every interaction, every collision, every gravitational exchange, every electromagnetic process. The law isn't upheld by any enforcement mechanism or any physical entity that monitors transactions. It's upheld because the universe obeys rotationally symmetric laws, and mathematically, symmetric laws have no choice but to conserve the corresponding quantity. But here's the gap that Noether's theorem opens rather than closes. Noether's theorem explains why angular momentum is conserved once it exists. It doesn't explain where it came from. Conservation is a statement about dynamics, about how things change over time. Initial conditions are separate. The laws of physics could be perfectly rotationally symmetric and therefore perfectly conserve angular momentum, while starting from a universe that had zero angular momentum, or a universe that had 1 trillion times more angular momentum than our universe appears to have, or a universe with a specific non-zero net angular momentum pointing in some particular cosmic direction. The symmetry dictates what happens to the angular momentum once it's there. It says nothing about the initial deposit. This is a general problem in physics, not specific to angular momentum. The laws of physics describe the evolution of systems from their initial conditions. But the initial conditions themselves are, in a deep sense, outside the laws. The standard model of particle physics doesn't predict the mass of the electron from first principles. It accepts the measured mass as a free parameter and incorporates it into the theory. General relativity doesn't predict the total mass-energy content of the universe. It accepts whatever matter exists and tells you how spacetime curves in response. The initial conditions of the universe, the specific values of all physical quantities at the earliest moment we can meaningfully discuss, are inputs to the theory, not outputs. They're the boundary conditions on the equations, not solutions produced by the equations. This isn't a failure or incompleteness of the theories, exactly. It may simply be the nature of physical law. Theories describe regularities in the evolution of systems, and initial conditions are, by definition, prior to evolution. But it means that the question of why the universe started with the angular momentum it started with, whether that's zero, slightly non-zero, or something more complex, isn't currently answerable from within our existing theoretical frameworks. Not because we haven't been clever enough, though perhaps cleverness will eventually help, but because the answer may require a fundamentally different kind of physical theory, one that addresses the origin of initial conditions rather than just their evolution. Some proposals exist. The Hartle-Hawking no-boundary proposal in quantum cosmology suggests that the universe didn't have a boundary in time, that it emerged from a quantum geometry with no singular beginning, and that the initial conditions were, in some sense, self-selected by the requirement that the universe be quantum mechanically self-consistent. If such a picture is correct, the angular momentum content of the universe might follow from the geometry of the quantum birth, and calculating the expected angular momentum would be a well-posed problem within quantum cosmology. Whether it would give the answer zero, and whether the proposal itself is correct, are both open questions. What is not open is this: the answer to why everything spins cannot be found in the conservation laws themselves. Noether's theorem tells you that the spin will be preserved. It's silent on why there was any spin to preserve. Part 14. Spin networks and space-time emergence. We've spent this documentary tracing rotation from the largest scales down to the smallest. Galaxies turning over hundreds of millions of years. Solar systems forming from rotating protoplanetary disks. Atoms broadcasting the signature of quantum spin across the radio spectrum. Electrons carrying intrinsic half-integer angular momentum as a relativistic necessity. At every scale, we found rotation. At every scale, we found angular momentum conservation. And we found that the origin of the angular momentum at each scale was inherited from the scale below, all the way down to the quantum level, where spin is baked into the definition of particles themselves by the structure of relativistic quantum field theory. But what if we've been asking the relationship backwards? What if spin doesn't exist inside space-time, with space-time providing the stage on which particles spin and orbit? What if space-time itself is built from something like spin? If the geometry of the universe is an emergent structure arising from something more fundamental, something algebraic and rotational at its core? I want you to sit with that for a moment, because it's a genuinely radical inversion. The entire documentary up to this point has treated space as the container and rotation as the content. Galaxies rotate inside space. Electrons spin. Inside atoms, inside space. Angular momentum is a property that things inside the universe carry around with them. But what if that framing is wrong at the most fundamental level? What if the container is built from the content? What if space isn't where spin happens, but what spin becomes when you zoom far enough out? This isn't science fiction. It isn't a fringe idea sketched on a napkin by someone who read too much philosophy. It's a serious, actively developed program in quantum gravity research pursued by some of the most rigorous mathematical physicists working today. The framework is called loop quantum gravity, and it was developed primarily by Carlo Rovelli and Lee Smolin starting in the late 1980s. Loop quantum gravity is an attempt to do something that has resisted every effort for nearly a century: to quantize general relativity, to apply the principles of quantum mechanics to the fabric of space-time itself, to treat geometry the way quantum mechanics treats matter and energy, as something that comes in discrete packets at the smallest scales, rather than as a smooth, infinitely divisible background. The result is a picture in which space isn't a smooth, continuous medium. Space is, at the smallest scales, a discrete network. Specifically, it's something called a spin network. A spin network is a mathematical graph, a collection of nodes connected by edges, in which each edge carries a label. That label is a value of quantum spin, not the spin of any particular particle, just spin as a pure mathematical quantity assigned to the connections between nodes in the network. And here's the part that should make you pause. The spin values on those edges aren't decorative labels. They aren't just bookkeeping. They are the geometric properties of the space the network represents. The area of a surface in the network is determined by the spins of the edges that cross it. The volume of a region is determined by the spins of the nodes contained within it. Both area and volume are quantized in loop quantum gravity. They come in discrete smallest units, the way energy comes in discrete photons or electric charge comes in discrete units of the electron charge. These smallest units of area and volume are set by the Planck scale, approximately 10 to the power of minus 35 meters, which is so incomprehensibly small that if an atom were magnified to the size of the observable universe, a Planck length would still be smaller than an atom. Below the Planck scale, the concept of smooth space breaks down entirely. There is no smaller spatial structure to speak of. Space isn't a continuous medium that can be divided infinitely finely, the way you might imagine endlessly zooming into a mathematical plane and always finding more plane. It's a network of discrete quantum spin values, finite and granular at the bottom, and the apparent smooth geometry of space at the scales we experience, from the millimeter scale of everyday life to the megaparsec scale of cosmology, is an emergent approximation. It's the macroscopic smoothness that arises when you average over an enormous number of discrete, quantized, spin-bearing edges and nodes. The same way the smooth surface of water emerges from the collective behavior of an enormous number of individual molecules that are individually anything but smooth. The implication of this, if it's correct, is extraordinary and slightly vertiginous. Spin isn't a property of particles existing in space-time. Spin is the raw material from which space-time is constructed. The angular momentum labels on the edges of spin networks aren't describing the behavior of matter within a pre-existing geometric background. They are the background. When loop quantum gravity says that space is a spin network, it's saying that what you experience as the three-dimensional geometry of the room you're sitting in, the distances, the volumes, the angles, is an emergent averaging out of an underlying structure made entirely of quantum angular momentum relationships. Space is organized quantum angular momentum. That's what it is at the bottom. There's a related, though technically distinct approach that arrives at a similar conclusion from a completely different direction. It's called twistor theory, and it was developed by Roger Penrose starting in the 1960s. Penrose's motivation was different from Rovelli and Smolin's. He wasn't primarily trying to quantize gravity. He was trying to understand why, The mathematics of quantum mechanics and the mathematics of space-time geometry seem to speak such different languages, and whether there was a more fundamental mathematical structure that would make both of them feel natural and unified. What he found was that you could describe the fundamental objects of physics, particles and their interactions, not in terms of points in space-time, but in terms of objects he called twistors, which encode a combination of momentum, energy, and angular momentum as a single geometric object. In twistor space, the primary objects aren't events at locations in space and time. They're null rays, light rays, along with their associated angular momentum. A point in space-time corresponds not to a fundamental object in twistor theory, but to an entire sphere of twistors. Space-time events are secondary, derived structures that emerge from the intersection of twistors. Reality, in the twistor picture, is built from spinning, directed structures, and the space-time we perceive, the four-dimensional stage of events and intervals that feels so fundamental to our experience, is a reconstruction of those structures at a coarser level. The spinning is primary, the space is the projection. Twistor theory had a complicated history. For decades, it was a beautiful mathematical framework that struggled to describe the full range of physical interactions, particularly the strong nuclear force. Then in 2003, Edward Witten showed that string theory amplitudes could be reformulated elegantly in twistor space, and the framework experienced a remarkable renaissance. Modern amplitude calculations in particle physics, the computations that predict the outcomes of particle collider experiments, are now routinely performed using twistor-inspired methods that are orders of magnitude simpler than the traditional Feynman diagram approach. The mathematics of twistors, built around angular momentum as a foundational object, turns out to be the most efficient language for describing particle interactions that physicists have found. Both of these approaches, loop quantum gravity and twistor theory, share a provocative common idea, arrived at from different starting points by different methods. The rotation and angular momentum we observe in the physical world aren't features imposed on a pre-existing spatial stage. They are, in some sense, prior to that stage, constitutive of it. The geometry of space doesn't provide a background in which quantum spin happens. Quantum spin, in its most fundamental algebraic form, provides the structure from which the geometry of space emerges. The universe isn't a place where things rotate. Rotation, at the deepest level, is what the universe is made of. If any version of this is correct, it completely reframes the question we started with at the beginning of this documentary. We asked, why does everything in the universe spin? We expected the answer to be about initial conditions, or conservation laws, or some primordial mechanism that set things rotating in the beginning. But if spin is more fundamental than space, if spatial geometry is built from spin networks, if spacetime is an emergent approximation of a more fundamental rotational algebra, then the question dissolves into something deeper and stranger. Everything spins not because spinning things were placed into a universe and happened to rotate. Everything spins because rotation, angular momentum, and spin are what the universe is made of at its most fundamental level. Asking why things spin in this picture is like asking why matter has extent. It doesn't happen inside space. It is what space is built from. Now, to be honest with you, and I think you deserve that honesty after coming this far, this is speculative. Loop quantum gravity and twistor theory are both incomplete theories. Neither has made confirmed experimental predictions at the scales where their specific features would become directly observable. The Planck scale is 16 orders of magnitude smaller than anything a particle accelerator can currently probe. We aren't going to be testing spin network geometry in a laboratory next year, or next decade, or perhaps in this century. We can't confirm or rule out these pictures directly, but they represent the serious frontier of what physicists are genuinely, rigorously exploring as possible answers to the question of what space, time, and matter actually are at their most irreducible level. And at that frontier, the answer keeps coming back the same way. Spin, not as a property inside reality, but as the structure of reality itself, all the way down. Part 15. The collapse problem across all scales. There's a humbling pattern in astrophysics that becomes clear once you look for it, and once you see it, you can't unsee it. At every scale where angular momentum plays a decisive role in shaping structure, star formation, planet formation, galaxy formation, black hole accretion, our theoretical understanding is incomplete in the specific details of how angular momentum gets redistributed. Not incomplete in the way that we're missing a few decimal places of precision. Incomplete in the way that we cannot yet predict, from first principles, something as fundamental as how fast a newly formed star will be spinning when it finishes forming. We understand the conservation law perfectly. We understand that the total angular momentum going into a process must equal the total angular momentum coming out. What we don't always understand in quantitative detail is the machinery by which angular momentum moves around inside that process. Who carries it? How fast? By what mechanism? And to where? This might sound like a minor technical gap. It's not. It's a gap that shows up at every scale we've examined in this documentary, from the birth of individual stars to the architecture of the largest structures in the universe. And the consistency of that gap, the fact that the same fundamental limitation appears whether you're studying a collapsing cloud of gas a few light years across or a galaxy cluster spanning tens of millions of light years, tells you something important. It tells you that angular momentum redistribution isn't a solved problem with some engineering details left to fill in. It's an active, open frontier of physics at essentially every scale simultaneously. Take star formation because it's the cleanest and most studied example of the problem. A molecular cloud collapsing to form a star starts with a measurable angular momentum. You can observe the cloud, measure the velocities of the gas across it, and calculate the total angular momentum contained in the system. Then the star forms. And when you measure the angular momentum of the newly formed star, you find something that should make you stop and think. The angular momentum is many orders of magnitude smaller than what the cloud started with. Not a little smaller, not half as much. Orders of magnitude smaller, meaning factors of 10 stacked on top of each other, separating the angular momentum of the cloud from the angular momentum of the star that formed inside it. This is called the angular momentum problem in star formation, and it has been known for decades. If angular momentum were conserved perfectly during the collapse with no mechanism to move it somewhere else, the result wouldn't be a star. The collapsing material would spin faster and faster as it contracted. Just as we described earlier in this documentary, the same ice skater effect, the same conservation law amplifying rotation as the radius shrinks. The material would spin so fast that centrifugal effects would halt the collapse long before stellar densities were reached. You'd end up with a large, rapidly rotating disk with no star at the center. The angular momentum has to go somewhere. Something has to carry it away from the forming star, or the star simply can't form. Several mechanisms are invoked by astrophysicists, and the honest description of all of them is that they're partially understood. Magnetic braking is one. The collapsing cloud is threaded by magnetic field lines, and as the cloud contracts, those field lines get dragged inward. But magnetic fields resist being compressed. They have tension along the field lines, and this tension acts like a lever arm, transferring angular momentum from the inner collapsing material outward along the field lines into the surrounding, slower rotating medium. The inner material loses angular momentum. The outer medium gains it. The books balance. But predicting exactly how efficiently this works under the conditions of a real molecular cloud, with real turbulence and real variations in density and magnetic field strength is a calculation that pushes the limits of even modern supercomputer simulations. Gravitational torques from a binary companion are another mechanism. Most stars don't form alone. Observations suggest that the majority of Sun-like stars form in binary or multiple systems, and the gravitational interaction between two forming stars in the same cloud can transfer angular momentum between them on timescales relevant to the formation process. Outflows and jets are a third mechanism, and these are spectacular. Young stars still embedded in their accretion disks launch powerful collimated jets of material perpendicular to the disk plane at speeds of hundreds of kilometers per second. These jets are observed in star-forming regions throughout the galaxy, glowing in infrared and radio wavelengths, extending for light years beyond the forming star system. They're carrying angular momentum with them, threading it outward into the surrounding medium at high velocity, acting as an exhaust valve for the angular momentum that can't be absorbed by the star itself. And then there's disk accretion, in which material doesn't fall directly onto the star but spirals inward through the disk, while angular momentum is transported outward through the disk by turbulent viscosity and magnetic instabilities, specifically a process called the magnetorotational instability, which makes the disk turbulent in a way that effectively moves angular momentum outward while mass moves inward. All of these mechanisms are real. All of them are observed. All of them are operating simultaneously in real star-forming systems, interacting with each other in complex non-linear ways. And none of them is understood in sufficient quantitative detail to allow a physicist to take the initial conditions of a molecular cloud core and calculate, with confidence, the final spin rate of the star that emerges. The angular momentum of stars at formation remains an area of genuinely active research, with new observations from facilities like the Atacama Large Millimeter Array revealing structures in protostellar disks that are still being interpreted and modelled. The same fundamental problem appears when you zoom out to the scale of galaxies. Galaxies have specific angular momenta, specific amounts of rotation per unit mass, that are correlated with their masses and their positions relative to the cosmic web, the large-scale network of filaments and voids that organizes matter at the largest scales of the universe. Simulations of galaxy formation can reproduce the broad statistical properties of angular momentum in galaxies reasonably well, but the details are sensitive to how the simulations handle feedback processes, the energy and momentum injected into the surrounding gas by supernova explosions, stellar winds, and the jets and radiation of active galactic nuclei. These feedback processes aren't calculated from first principles in galaxy formation simulations. They're handled through approximate prescriptions tuned to reproduce observed properties, because calculating them from first principles would require resolving scales from individual stellar explosions up to entire galaxies simultaneously, which exceeds the capacity of any computer that exists or is likely to exist in the near future. Whether the spin of a particular galaxy can be reliably predicted from the initial conditions of its host dark matter halo, and whether the observed alignments of galaxy spins with cosmic web filaments are fully captured by current models, are questions that a substantial fraction of the computational astrophysics community is actively working on right now. Come down to the scale of individual planets, and the problem takes on a different character but persists. The Earth-Moon system has a specific angular momentum budget, a total amount of angular momentum in the Earth's spin and the Moon's orbit combined, that constrains theories of how the Moon formed. The favoured hypothesis is the giant impact model, in which a Mars-sized body called Theia struck the early Earth in a glancing blow roughly 4.5 billion years ago, ejecting an enormous amount of molten material that eventually coalesced into the Moon. This model has to explain not just why the Moon has a composition very similar to the Earth's mantle, and not just why the Moon has relatively little iron compared to the Earth, but also why the Earth-Moon system has the specific total angular momentum it has today. Some giant impact simulations reproduce that angular momentum naturally. Others require quite specific choices of impact angle, impact speed, and the masses of the two colliding bodies to get the numbers right. The parameter space is large and the constraints are real. And the question of exactly what kind of impact produced our moon is still not fully settled. And the moon, it turns out, is still actively redistributing angular momentum in the Earth-Moon system right now. Tidal interactions between the Earth and Moon are transferring angular momentum from the Earth's rotation to the Moon's orbit at a measured rate. The Moon is receding from the Earth at approximately 3.8 centimeters per year, a rate measured precisely by bouncing laser pulses off retroreflectors left on the lunar surface by the Apollo missions. The Earth's rotation is correspondingly slowing down by about 1.4 milliseconds per century. Billions of years ago, the Moon was dramatically closer, perhaps a third of its current distance, and the Earth was rotating much faster, a day lasting perhaps 6 hours instead of 24. The tidal dissipation was correspondingly much more intense. Reconstructing the full history of this angular momentum exchange from the moment of the giant impact to the present, and using that reconstruction to constrain the original impact conditions, is a project that involves geologists studying ancient tidal rhythms preserved in sedimentary rocks, astronomers measuring the current recession rate, and dynamicists modelling the coupled evolution of the Earth's spin and the Moon's orbit over billions of years. It's in every sense an ongoing investigation. The pattern across all these scales, stellar, galactic, planetary, is consistent and striking. The conservation law holds everywhere it's been tested. Angular momentum is accounted for at every scale. What goes in must come out. But the specific physical mechanisms that carry angular momentum from one part of a system to another, the magnetic braking, the turbulent viscosity, the tidal coupling, the jets and outflows, the disk instabilities, are only partially understood in quantitative terms. We know the ledger is balanced. We're still mapping out in detail every account in the ledger and every transaction between them. And here's what I find genuinely remarkable about that. This isn't a failure of physics. It isn't evidence that something is wrong with the underlying theory. The conservation law provides an exact constraint, and within that constraint, the research program is to understand the mechanisms, the plumbing, if you want a metaphor, that move angular momentum around. That's normal science working at the edge of what observation and computation can currently resolve. What's remarkable isn't that the edges are incomplete. What's remarkable is how far the same single principle carries you. Angular momentum is conserved. Spin persists. Rotation accumulates rather than dissipates in gravitationally bound systems. That one law, applied consistently across 20 orders of magnitude in physical scale, from structures at the Planck length all the way up to the filaments of the cosmic web, reproduces the architecture of everything we can see. The same mathematical relationship that keeps an ice skater spinning when she pulls her arms inward is the relationship that keeps the Milky Way turning at 230 kilometers per second, billions of years after the gas cloud it formed from has long since been consumed, dispersed, and built into stars. One law, 20 orders of magnitude, every spinning thing in the observable universe. The ledger always balances. We just don't always know yet exactly how. Thus, Part 16, Final Synthesis, the Unresolved Universe. Let's take stock of what we know, what we think we understand, and what remains genuinely, openly, without apology, mysterious. Because after everything we've covered in this documentary, the rotating planet carrying you eastward at over 1,000 miles per hour, the quantum spin broadcasting from every hydrogen atom in your body, the flat rotation curves of galaxies pointing toward invisible mass, the Stern-Gerlach experiment splitting silver atoms into two impossible beams, the Pauli exclusion principle holding the floor solid beneath your feet, Gödel's rotating universe swallowing its own timeline. After all of that, we owe ourselves an honest accounting, not a tidy resolution. Physics doesn't always offer those, but an honest inventory of what the ledger actually says, line by line, before we close it. Every particle in the universe has spin. Every electron, every quark, every neutrino, every photon carries an intrinsic quantum angular momentum that's a fixed, immutable property of its type. Not acquired through some process, not borrowed from somewhere else and eventually returned. Not the result of the particle spinning up at some point in its history. The spin is part of what the particle is, encoded in its definition as completely and permanently as its mass or its electric charge. It's demanded by the mathematics of relativistic quantum field theory, not as an optional feature that theorists chose to include, but as a necessary consequence of combining quantum mechanics with special relativity. The Dirac equation does not accommodate a spinless electron. The electron's half-integer spin falls out of the mathematics whether you want it to or not. And that spin is conserved in every interaction the particle undergoes, from the moment those quantum fields were excited in the earliest moments of the universe's existence to the present moment and forward into whatever future the universe has remaining. Not one unit of that spin has been created or destroyed in the entire history of the cosmos. Every bound gravitational system in the universe rotates. Every planet orbits its star and spins on its axis. Every star rotates faster when young and slower as it ages and sheds angular momentum through its stellar wind, but never stopping. Every binary system orbits its common center of mass in an endless gravitational waltz that will continue until gravitational wave emission carries the energy and angular momentum away. And even then, the merger product will itself be a rapidly spinning object. Every galaxy rotates. Every galaxy cluster contains galaxies orbiting their collective center of mass. Every structure in the universe that formed under gravity from a precursor that contained any angular momentum at all has inherited, amplified, and preserved that angular momentum through the entire process of its formation and evolution. The disk structures scattered throughout the observable universe, the rings of Saturn, the planetary systems around other stars, the accretion disks around neutron stars, the majestic spiral disks of galaxies, the blazing accretion disks around supermassive black holes at the centers of quasars visible halfway across the universe. All of these are physical records of angular momentum that couldn't be absorbed into the central structure and instead organized itself into the flattest, most rotationally efficient geometry available. Every disk is a fossil. Every ring is a memory. Every spiral arm is angular momentum writing its own history in starlight. The conservation law that governs all of this is one of the most precisely tested laws in all of physics. It says that angular momentum is neither created nor destroyed in any physical process, anywhere, ever. It follows, as Emmy Noether proved in 1915 from the rotational symmetry of the laws of nature. The fact that the laws of physics don't have a preferred direction, that an experiment gives the same results regardless of which way it's oriented in space. That symmetry is exact, as far as any measurement has ever been able to determine. And because the symmetry is exact, the conservation law is exact. Every experiment ever performed, in particle accelerators, in atomic physics laboratories, in astronomical observations of spinning pulsars and orbiting binary stars, is consistent with this conservation law, not approximately consistent, not consistent within experimental error, exactly consistent. The precision of tests of angular momentum conservation in particle physics reaches parts per billion or better. The law holds everywhere it's been tested, at every scale, in every interaction, without a single confirmed exception in the entire history of experimental physics. And yet, here's the number that should make you set down whatever warm drink you poured at the beginning of this video and just think for a moment. The total angular momentum of the observable universe, as best as cosmologists can measure, is zero. Not small, not negligible compared to the sum of all individual angular momenta. Zero, in the sense that the positive angular momenta and the negative angular momenta cancel each other with a precision so extraordinary that no measurement has ever detected a residual. Every spinning galaxy has a statistical counterpart spinning in the opposite direction. Every clockwise orbital motion in a galaxy cluster is balanced by counterclockwise orbital motion somewhere else. The cosmic microwave background, the oldest light in the universe, the thermal afterglow of the hot early cosmos that fills the sky from every direction, shows no preferred rotation axis, no asymmetry that would indicate a global spin. The large-scale structure of the universe is isotropic to a precision that rules out any significant global rotation. 2 trillion galaxies, each one spinning, orbiting, precessing, buzzing with the intrinsic spin of every particle they contain, and the vector sum of all of it cancels to nothing. We don't know why. We don't know whether the cancellation is exactly zero or merely very close to zero. The difference between those two options matters enormously, as we discussed when we talked about Gödel's rotating universe solution, but our measurements can't yet resolve it. We don't have a theoretical principle that requires the universe to begin with zero net angular momentum. There's no law written anywhere in physics that says the initial conditions of the cosmos must be rotationally neutral. We have no confirmed theory of quantum cosmology, no working model of the quantum birth of the universe that derives this cancellation from something more fundamental and hands it to us as a prediction. The zero is observed. It isn't explained. The books balance perfectly, and nobody knows who designed the accounting system. We know from Gödel's work exactly what's at stake in that zero. A universe with significant net angular momentum isn't just a faster spinning version of our universe. It's a qualitatively different kind of universe. One in which the causal structure of spacetime itself is altered. Closed time-like curves become geometrically possible. Paths through spacetime that loop back to their own starting point, allowing a traveler to return to events that, in our universe, are permanently and irreversibly in the past. The arrow of time, the one-way flow from past to future that underlies thermodynamics, entropy, memory, causality, the entire structure of how events relate to each other, that arrow depends on the causal structure of space-time being clean and consistent. In a rotating universe, it might not be. Whether our universe is near zero angular momentum is a necessary prerequisite for the existence of time as a coherent, directed dimension. Whether complexity, chemistry, biology, and consciousness require a non-rotating cosmos in order to be possible at all, is a question that sits at the intersection of physics, cosmology, and philosophy, and it doesn't currently have a settled answer. But it isn't an idle question. It's the kind of question that, once you've followed the thread this far, you realize was always implicit in the story, waiting at the end of it. We know from the spin statistics theorem and the Pauli exclusion principle that the half-integer spin of fermions is the foundation on which all physical structure rests, the reason matter occupies space, the reason atoms have distinct electronic shells, the reason the periodic table has the structure it has and not some other structure, the reason chemistry exists as a subject with more than one element in it, the reason the floor you're standing on holds your weight, the reason white dwarfs and neutron stars resist the gravitational collapse that would otherwise compress them into black holes. All of this, every material structure in the observable universe, every piece of chemistry, every biological organism, every planet, every star that doesn't immediately collapse, rests on the antisymmetry of fermionic wave functions, which rests on the half-integer spin of fermions, which rests on the structure of relativistic quantum field theory. Spin isn't a curiosity at the edge of particle physics. It's the load-bearing element of physical reality. Remove it, and everything falls through everything else into a featureless, structure-free plasma. Keep it, and you get the universe as it actually is, layered, structured, chemically complex, and eventually, improbably, self-aware. We know from loop quantum gravity and twistor theory that some of the most serious and mathematically rigorous approaches to the deepest problems in physics suggest that spin isn't a property of matter existing within space, but is the fundamental structure from which space itself is constructed. That the geometry you perceive as the three-dimensional room around you is an emergent macroscopic averaging of a discrete quantized network of angular momentum relationships operating at the Planck scale. That spacetime isn't the stage on which spin plays out, but the audience watching a performance made entirely of spin. If any version of this picture is correct, and we can't yet confirm or rule it out experimentally, then asking why everything in the universe spins isn't a question about the contents of reality. It's a question about what reality is made of, and the answer is spin. Asking why things spin is like asking why matter has spatial extent. It doesn't happen inside space. It's what space is built from, and we know from the entire arc of this 2-hour journey that the question of why everything spins has two distinct layers that physics treats in completely different ways. The first layer, why spinning things keep spinning, why angular momentum is conserved with perfect fidelity, why every gravitationally bound system naturally organizes into rotating structures, why disks form instead of spheres, why the ice skater spins faster when she pulls in her arms, why the Milky Way will still be turning long after the sun has died, is answered. The answer is Noether's theorem, rotational symmetry, conservation of angular momentum, the physics of collapsing gas clouds, accretion disk dynamics, tidal torque theory. The mechanisms are understood, at least in their broad outlines. The conservation law is exact. The math works. The predictions match the observations. This layer is one of the great achievements of human understanding, a single mathematical principle rooted in the symmetry structure of space-time that explains the rotation of everything from a spinning top to a spiral galaxy. The second layer is different. Why did the universe begin with the angular momentum it began with? Why did the initial conditions of reality contain spin at all, rather than starting from a rotationally empty state? Why is the net global angular momentum so close to zero? And is it exactly zero or merely approximately zero? And if it's merely approximately zero, what is holding the residual in place? And what would happen if it were released? These questions aren't answered, not partially answered, not answered in principle with technical details remaining to be calculated. They are genuinely, fundamentally, presently beyond the reach of the physical theories we currently possess. They point toward the boundary of what physics, as currently formulated, is even capable of addressing, toward the question of initial conditions, of why the universe started as it did rather than some other way, which is a question that the laws of physics describe the evolution of systems rather than their origins. Physics, in its current form, is an extraordinarily precise description of how the universe's rotational content evolves from whatever initial state it began in. It cannot tell you what determined that initial state. Every calculation, every conserved quantity, every elegant application of Noether's theorem, every triumphant prediction of the Standard Model and general relativity takes as its starting point the assumption that there was something to begin with. Some initial angular momentum, some initial spin distribution, some initial rotational content to preserve and redistribute through the subsequent history of the cosmos. The laws describe the evolution flawlessly. The origin of the thing being evolved remains outside the frame. Every particle has spin. Every structure rotates. The universe, taken as a whole, does not spin. Every piece spins. The whole does not. That sentence is either the most elegant fact in cosmology or its most glaring open wound, depending on how you look at it. Possibly both, simultaneously. In the space between those facts, in the gap between the perfect bookkeeping and the absent origin story, between the conservation law that holds everywhere and the initial condition it cannot explain, lies one of the deepest unsolved problems in all of physics. Not a technical problem of precision or computation, a conceptual problem about what kind of answer we are even entitled to expect when we ask why the universe is the way it is rather than some other way. Whether that question has an answer within the framework of physics, or whether it requires a new kind of understanding we haven't yet invented, is itself an open question. The universe has been spinning since before time had a name for itself. Every galaxy in the sky is a wheel that has been turning since before the Earth existed. Every star is a gyroscope preserving angular momentum inherited from a cloud of gas that predated the solar system. Every atom in your body is broadcasting the signature of quantum spin at 1.42 gigahertz, quietly and continuously, into a universe that is, in some sense, made of the same thing it is announcing. And somewhere in that machinery, in the spin networks that might be the fabric of space, in the initial conditions that seeded every rotation we've traced from the quantum to the cosmic, in the impossibly precise zero that keeps the causal structure of time intact. Somewhere in all of that, there is a question that the universe has been carrying since its first moment and has not yet answered. Not because we haven't been clever enough, though perhaps cleverness will eventually help. Not because the instruments are too crude, though better instruments will certainly be built. Not because the mathematics is intractable, though the mathematics at this frontier is genuinely hard. But because the question reaches past the edge of what the laws of physics, as currently written, are structured to address. The laws describe what happens to spin. They don't describe where spin came from. They keep the books with absolute fidelity across the entire history of the cosmos, but they have never shown us the first deposit. And they may not be the right kind of tool for finding it. We know how the universe spins. We know that it cannot stop. We know that adding everything up gives you, impossibly, nothing. And every time a galaxy turns, every time an electron broadcasts its quantum signature into the void, every time the Earth carries you silently eastward at 1,000 miles per hour through a night that feels completely still, that stillness isn't emptiness. It's the universe, perfectly balanced, spinning on a question it has been asking since before there was anyone around to wonder.